Welcome back to Physics with Miyoshi, and today we're going to talk one more problem on kinematics in two dimensions. And what we want to do today is if we had maybe we had a football getting kicked, or we have a baseball flying out, or we have some object being thrown or tossed or kicked or projected somehow on a projectile motion. And in this case, we have a object going at 22 meters per second at an angle of 40 degrees, and we want to know both the height would go and the range. It would go all the way until it hits the ground at the same level it started at. So first thing we're going to do is we're going to find both the x initial velocity, which will also be our final, and the y as well. So we're going to use our definition of cosine and sine. So we know that cosine of theta is Vox divided by V0. And we know that sine of theta is VOY divided by VO. So from that we can then say that Vox is V0 cos theta, and V0y is V0 sine theta. And I already did all those calculations, and found that they are in the x direction we have 16.85 meters per second, and in the y direction we have 14.14 meters per second. Okay? So again, that's just the definition of sine and cosine, and we can then rearrange the equation. So, let's put those guys up here, in case I need to erase stuff. Vox 16.85 and 14.4 meters per second. Okay, now what do we do? Well, we want to find the time that it takes to get to the top. So, oftentimes if you just try to calculate, you're not going to have any height difference here usually. You might have some over here, either above or below, but in this case we're going to the same height. So instead of trying to use that, because then it's a y change of 0, and we have the same velocity at both ends, we want to break up this problem to be just half. So how am I going to get to the top? Well, let's look at this as v at the top. And at least in the y direction, we know that the top is going to have 0 meters per second. Because at the top, it's got to change from going upward to coming downward. So if we want to do this, we can do it one of two different ways. One way we could do it is considering that it's going up, and the other way we could do it is we could consider it going down. So I'm going to do it both ways, and what I'm going to use is this equation down here. So in this case, I'm going to have y is v0 times t plus 1/2, oops, this is in the y direction, 1/2 a in the y direction, t squared. Okay? I don't know what y is. I don't know what t is, but I can find... Oops, that's not the one I want to use. Yeah, it is the one I want. Okay? Oh, I gotta do one other thing first. Let's slow down here. Back up the horse. Before I do that, I need to find the acceleration, or the time, and I could do that by just a in the y direction is delta v over in the y direction over delta t. And then since I know the acceleration due to gravity is the y, and I know the v0, or the initial and the final, what I can do is rearrange this equation so that time is vf in the y minus v0 in the y. Divide that by g, and I can figure that guy out. The final is 0 minus y is 14.14 meters per second. Divide that by negative 9.8 meters per second squared, and I end up getting the time. Notice that the negative signs will give me a positive. Divide by negative 1 by negative 1 to get positive 1. And I end up with my time is 1.44 seconds. Now that is just the time to the top, so I'll just put that to the top. Maybe I'll put that in parentheses just to remind myself. Okay? So that's just the time it takes to get to the top. T is 1.44 seconds. Now, what I'm going to do with that is now I can use that equation I just wrote up there and erased to find my height. So, now I can use y is v0t plus 1/2 at squared. And in this case, my v0t, I'll use a v0y. It's y. And that was 14.14 meters per second. My time is 1.44 plus 1/2 negative 9.8 meters per second squared. That negative is very important here, and you'll see in a moment. Times my t, which is 1.44 seconds, quantity squared. And now if I do all this math, it ends up being 20.405, what is that? Meters minus 10.2, we'll just get rid of this guy there, meters, which will give me 10.2 meters. That's if I go up. I can also do the same problem considering this top point to be my v0 and the bottom to be my final velocity. So in that case I would have y is v0y, which would be t plus 1/2 at squared. In that case, this guy would be 0. That guy is still what it was up here, 1/2 negative 9.8 meters per second squared times t squared, which is 1.44 seconds squared, which will give me 10.2 meters, which is exactly, actually now it's a negative though. And the negative just tells me that it fell from the top down to the bottom. Notice that they are the same except for the negative sign. One just says it's going up, and the other one says it's going down. But they should be the same quantity. Okay? And then the last thing we want to do with this guy is find out what the range is, this distance here. And that is merely a matter of knowing what my average velocity in the x direction is. So, if I think about this equation over here, v average is delta d over delta t. I can rearrange that guy to be delta d is v average times delta t. So my average in that, this is in the x direction. So in the x direction, my VOX was 16.85. Oopsie, meters per second. And my time is not 1.44 seconds because that's the time it takes to get up to the top. It would be multiplied by 2, so that would be 2.88 seconds. And that guy would then be, whatever it is, 40, oopsie, that can't be right. Yes, it is. 48.64 meters. Okay, that's going to be my total range, if you will. And one other thing to notice, and this is really critical when you start solve these problems, the one thing that stays the same, because it is the same object, is the time stays the same. Even though we have to do two problems essentially calculating for the x and the y, the time is what stays the same because the object is the same object. So, there you have it. Knowing the initial velocity, including the angle, we can break this problem up into x and y. Notice that we could also change this guy, and I'm not going to do this right this moment, but if we have a height difference here or a height difference here, we could also do the same problems. We would just have to do going up and going down as two separate problems. So we actually kind of almost do three problems to solve one big problem in kinematics in 2 dimensions. So hopefully you realize that these same equations that we used in one-dimensional kinematics are the same. Now we just have components and use a little vector stuff that we learned earlier too. So hopefully you realize that they're not that much different, just we have to break things down a little bit more. But that's problem solving, not just in physics, but all over the place. Break things down into smaller components. So hopefully you got a little bit more understanding of kinematics in 2 dimensions and how to solve some of these range and height problems. And thanks for tuning in again for Physics with Miyoshi.